Good morning. I will be speaking to you guys about music and more specifically sound processing techniques around music and what you can actually do with regards to changing sound clips that you might have access to. We will be going into specifically tempo-focused sound processing, which has to do with finding the beat of the music, which is not quite as simple as it may seem. And then afterwards, I will be going into various sound processing techniques around VSTs and what those can do for you in terms of changing pitch, volume, EQ, and various effects on your sound. What can we do with a beat? Or more accurately, why on earth would I want to find the beat in a piece of music? Well, there are several fun applications that you can do if you can find the beats in music. Some of those being having lights that strobe in time with your music so that your non-epileptic friends can have fun with you. Or perhaps a dancing robot that shows off sick moves. Or if you're in the bursary program last year, you might have heard of a program called the JS Joust, which was notoriously difficult to find the tempo of music to move your phone along to. To dive into this, we need to consider how sound is actually stored. There are various formats of sound, MP3, WAV, OGG, WMA, to name a few. All of these store sound as a series of samples taken of analog sound waves, which is stored as a pulse with an amplitude at a rate of 44,000 hertz. That's 44,000 times per second that they sample the sound. This obviously results in a huge amount of data that needs to be processed if we want to change the format of sound and how it actually behaves. In these sound files, we end up with a bunch of audio waves that all kind of get added together and end up more tangled than the headphones that we use to listen to them. Sound waves don't add together as one would expect and overlap, but rather they add together using a process called interference. Constructive and destructive interference specifically. Constructive interference results in the amplitude increasing, while destructive interference results in the amplitude of the signal decreasing. This results in weird sound waves like the bottom one on screen, which is a very simple musical chord. One can imagine seeing how complex this simple chord is when made up of three very similar sound waves up above it, that when we add together sound waves that are more complex, such as different musical instruments playing the same note, we will end up with a very big mess of a signal that is very difficult to disentangle. So we have a large amount of data stored in audio files, but is this information enough for us to actually find the tempo of the song? Can we calculate it? As it turns out, the answer is, well, yes, but actually no. See, the difficulty with finding tempo is that we as humans, when we listen to music, do it intuitively. That means we don't have a step-by-step method that we lay out to find the beat. We just sort of hear it. And that's very difficult to translate over into the computer space of pulses and amplitudes. And even though the pulses in the sound wave seem to have a frequency, that frequency doesn't actually correspond to the tempo. That frequency corresponds to pitch. The pitch of the music is determined by the frequency of the sound wave that makes up that particular sound, with higher frequencies being higher pitch. And so the frequency information that we can gather from a surface level from a sound file is not actually all that useful in terms of finding the tempo. The frequency that we need for the tempo is the frequency of pulses of the same frequency of sound. a frequency of frequencies. As such, it's difficult to calculate this information, but instead we can make an educated guess. Because of this, tempo processing and calculating the tempo can benefit from various AI and machine learning techniques, but you can make do without them. There are two methods that we can use to calculate tempo. One of them is to emulate our human way of doing it, which is to try and find a beat in the music. And the other one is a more mathematical oriented way, which is to filter the signals and to try and find the signal with the highest energy when filtered using a particular comb filter for various tempos. The trade-offs for these different beat detection and filtering detection algorithms is that in beat detection's case, it is a very computationally expensive operation because you have to pass the entire sound file made up of 44,000 samples per second for the entire duration of the song to try and detect beats in all of those samples. Filter tempo detection is a bit less intensive, but still very expensive as well. Filtering tempo detection can't handle tempo changes because it takes a small sample of the song to reduce the expensiveness of the computation. It also results in a measurement of your tempo, which is entirely separate from the song, which then has to be matched up with a beat at a later stage. The way you go about doing these algorithms. For beat detection, you need to take samples of your sound wave in groups of 1,024. And then you compare that to the previous second of sound and compare the average energies. If there's a spike in the average energy over a certain ratio, you can consider it a beat. This obviously then gives you beats associated with particular sound bites, which is useful for our case of needing the tempo associated with a specific point in time in the song. The filtering tempo detection is different in that we need to extract frequency bands from the song using a fast Fourier transform function, which will convert the signal to the frequency domain, which is less computationally expensive than calculating in the time domain. We then differentiate the signal by making the increases in amplitude sharper so that we can more easily compare it to the comb filter function, which is in essence an impulse train, which is a regular impulse, which is an amplitude on its own, followed by a zero value. It ends up looking, ironically, like a comb because it has prongs standing up. This results in various energy values compared to the tempo that we filter it with. And so the filter that provides the highest energy value is most likely to be the tempo of the actual song. Now we can move on to the less complex stuff, which is the pre-built solutions that VSTs tend to offer. What is a VST? A VST is a virtual studio technology. And what they attempt to do is to emulate what you can do with actual hardware that you would mix music with. So you can pass the music through gates, you can pass it through filters, you can add reverb, you can modulate the pitch. And we're going to go over how these VSTs actually do that. For pitch modulation, you need to adjust the frequency of the sound wave. Frequency of sound changes with a factor of 2 per octave. That is, a note, which is 1 octave below another note, is exactly half the frequency of the higher note. Along with the scale of music being 12 semitones to an octave, a semitone being the smallest commonly used gap between notes, That means that the exact ratio that you need to multiply a note by to increase its pitch by 1 semitone is 1.05 approximately, or the 12th root of 2. To change the volume of a sample, you need to pass it through a filter to decrease the amplitude of the music. The amplitude directly correlates to the volume of the sound produced, with a higher amplitude being a higher volume. EQ is similar in that you need to decrease the amplitude of very specific frequencies. You can do this with filters and gates. Noise suppression uses a gate technology, which is a filter that filters out various frequency bands that you don't want in your sound. And then we get to the effects, the cool stuff. There are effects such as reverb and phases, reverb being the effect of an echo that a room would produce, except added digitally. They do this by adding the same signal with a slightly lower amplitude very quickly after the original signal that is produced, and this produces an echo effect. A phaser is when the sound wave sort of warbles a bit. The pitch modulates up and down slightly, and that's done using a low frequency wave. And they basically use the interference property of waves to add that low frequency wave to the signal, which will modulate the signal with a very low or very long period rather. Thank you.